All right, with no further ado, Erica Fischer.
Okay, I'm back. So I'm going to tell you, I also don't have any plots in this one. I didn't realize we were supposed to have plots, but I'm just going to kind of keep it at a high level and tell you what we've been doing. I've been at Oregon State University for 6 years now, and I've been working with TDI in this field for the whole time with many of the faculty members that have been presenting today. And so I'm going to talk about where we've come, what's the story of timber and fire research within TDI, where we're going over the next few years. And then I'm going to have lots of time for Q&A because I really want to hear what the challenges are that all of you are facing within your designs, with AHJs, with concerns about safety, because that's really what fuels all of our research here at TDI. There we go. All right. So I first, in order to talk about timber and fire research, I want to get everyone on the same page of what we're looking at when we're doing this type of research. So all of you in the design fields have been working with hourly ratings. The way that these are developed is individual components are put into or on a gas-fired furnace. They're subjected to a singular time temperature curve, a singular fire demand. And the time it takes for those components to reach a critical behavior is the hourly rating. That is what you all are specifying within the International Building Code. Those critical behaviors are flame through, smoke through, or structural failure. Although structural failure very often does not control what that is. So if you notice, there's no structural engineering associated with this. There's no design associated with the hourly ratings. And so on the flip side, performance-based design for fire uses everything we know about structural engineering, everything we know about fire dynamics to develop a building-specific fire demand. If I wanted to calculate what the fire demand in this space is, I could. And I could perform a performance-based design and look at how the fire would spread within this space, what would happen to the windows, how egress could be enabled for everyone to get out. And we could also look at system level evaluation. So we could consider if one of these girders failed, could load be redistributed throughout the roofing system, or would that, spark, progressive collapse of the building. And so this is really where the research lies. Okay, so all of the research that I am doing and that we're doing at Oregon State University as it pertains to fire research falls under this performance-based design. How can we more fundamentally understand the behavior of mass timber in fire? How do we understand its pyrolysis and charring better? How do we understand fire dynamics within the mass timber environment and a mass timber building? So with that, now that you all understand fire and you're all fire experts, I'm going to tell you the story of fire research within TDI. And it's been really focused on these 4 segments. The first being timber concrete composite floors. We heard from Ian about all the amazing research that's happening on timber concrete composite floors, on all the different types of loading scenarios, as well as serviceability requirements. We tested a number of timber concrete composite floors in fire multiple times over the last 5 years, as well as perform finite element analysis and develop design solutions for timber concrete composite floors. We've tested a number of connections, both platform frame, balloon frame connections, as well as glulam beam to column connections, and I'll talk about those a little bit later in the presentation, both under a heating exposure for the fire, as well as in a cooling scenario after the fire, so during all phases of the fire demand. We have used Fire Dynamics Simulator to simulate fire within mass timber buildings, to simulate fires within mass timber compartments that have been tested all over the world. We've been able to simulate velocity measurements as well as heat fluxes and temperatures throughout these compartments and buildings, and then took all of that knowledge and applied it to mass timber buildings under construction to look at sequencing of applying fire protection and how we can incorporate that into the design process. So this is really where we've been going in our research. And I have education and outreach, and I'll talk about it at the end. And I know a lot of my colleagues have highlighted the students that are working on this project, but all of this research is funding students. It's funding the next generation of mass timber experts who are going out and working for all of you and bringing that knowledge into the field and bringing that excitement for mass timber into industry. And so we can't forget about them, because all of these research projects are developing new knowledge, but also new students and new experts in this field. So there are questions that are left to answer, a lot of questions. We've been looking mainly at the heating phase of fires. We haven't been considering smoldering of mass timber. How do we design a mass timber building for firefighter safety? How do we design a mass timber building for smoldering so that we can prevent further damage of mass timber during that decay phase of the fire? What about, we talked about LCA a lot. In fire, the emissions from a building contribute to the carbon and contribute to the environmental impacts. Water runoff from firefighter suppression systems are also contributing to the environmental impacts of fires. What are those emissions in a mass timber building? How do they differ from a building that's steel or concrete? How do they differ when you have protection versus no protection within the building? Protection meaning encapsulation, not sprinklers. And then, can we actually scale these experiments? Large-scale experimental testing is really expensive. I fly literally to another country to go do them. And so, can we actually learn from scaled experiments in fire? What can we learn, and how is that beneficial to moving this industry forward? And how can we do that maybe on OSU's campus with our new fire lab? So these are some of the remaining research questions. I am sure you all have many, many more, but this is really where I'm going to focus the remainder of my presentation to show how some of this previous research is fueling some of this future research that we're doing to answer these questions. So all this future research is in collaboration with a lot of you. And so I want to kind of highlight all of these amazing companies that have been consulting on our projects, as well as providing support for the projects, and hopefully hiring our awesome students. Okay, so now that you understand the prescriptive fire protection approach, performance-based fire protection approach, what we've done so far in fire, I'm going to talk a little bit about the decay phase of the fire and why this is really so critical. And so you heard this morning from Ian and Judith about how we're really supporting our local economy through all of this timber research. We're taking timber from Oregon forests, we're funneling them through Oregon companies, creating these mass timber products, we're putting them in our Oregon institutions. But are our timber buildings safe? And a lot of our research is really focused around that. We're focused on, is our timber buildings safe in seismic and fire? Are they durable? But from the fire side, I'm asking this question from the occupant safety as well as community safety with emissions from the fire, as well as smoldering for firefighter safety. So we know smoldering occurs, right? We are in the Pacific Northwest. I can probably guarantee 99% of us have been camping. And so we know that timber smolders. We know that the campfire smolders. Mass timber is no different, and it's not a bad thing. It happens, and we can't ignore it. And we need to make sure that we address it. We need to know where the smoldering occurs so that we can actually design for it. We need to know where the smoldering occurs so firefighters can identify it in buildings when they go in, and we can create a safe environment for everyone. So There's two experimental kind of regimes that have been going on that I'll dive into in a second, that have really been inspiring this future research that's going to be happening over the coming years. The first is smoldering behavior of platform frame and balloon frame construction, as well as fire behavior of glulam beam to column connections. In recent years, in all my fire experiments, we've been including a decay phase of the fire to just leave specimens on the furnace and continue to collect data so we can see what happens. The first project I'll talk about is in collaboration with Lech Mazinski, and this was funded through, the main project was funded through a USDA Wood Innovations grant. And this project tested balloon frame and platform frame connections, you see on the left, in a smaller scale setup on a furnace at the Western Fire Labs. The specimens were loaded and were exposed to 1 hour of the ASTM E119, which is the standard fire. We then shut the furnace off and just left it for an hour. Okay, our goals were, we wanted to look at what were the char rates during the heating phase and what were the char rates during the cooling phase. Do we actually see char progression during that hour of quote unquote cooling? And then how do these connections actually perform during the fire itself? And what we saw is that heat does begin to propagate through these connections. Equilibrium has to occur, right? So if it's cooler on the top surface of the CLT, heat will continue to propagate through the CLT, through the connection, so that we have that equilibrium of our temperatures. We saw combustion, that picture in the top right is flames that occurred 9 minutes into the cooling. So the furnace had been shut off for 9 minutes. There was no external combustion and flames occurred. We saw that there was very large temperature rise when we used steel elements within the connections. And then we also saw some really interesting behavior with the charring. We saw char compression. So in steel construction, we characterize our connection performance in terms of rotational capacity during a fire. But in mass timber, if we try to apply the same thing, we have rotation of the connections during the fire due to loading, due to just thermal degradation of the wood itself, due to the decrease of material properties. But then we also have compression of that char itself. And so we have both happening at the same time. So how do we differentiate between the two? What movement is from char compression? What movement is from just the structure itself? And so we had the opportunity to then perform another experiment on fire behavior of glulam beam to column connections. These connections were tested under deformation compatibility at OSU, and then we tested 3 connections under fire demands at the National Research Council in Ottawa, Canada. So I literally go to another country for these fire tests. This was in collaboration with Ari Sinha and KPFF and Holmes. We tested, again, 3 different types of connections. And the picture I'm showing here is after we subjected each connection to 1 hour of heating, and then we just shut the furnace off and we left it there for 2 hours. And that is what came out of the furnace. After 2 hours, it was still flaming. And so again, this isn't, I'm not saying this is a bad thing. Mass timber is great, but we need to understand this better so we can actually design for this. We can actually understand why this is happening and how to protect against it. So the 3 connections that we tested, I'm showing here on the left was a knife plate connection where the glulam beam was bearing on a steel knife plate that was then embedded within the glulam beam itself and screwed to the column. The one on the right is a pure bearing connection. So there was no mechanical fasteners between the beam and the column. And the last one was a double beam connection where 2 beams sandwiched a single glulam column, and there was a steel plate connecting all 3 together. We loaded the top of these specimens with a distributed load. This is why I go to another country, is their loading apparatus is fantastic. And then we subjected the specimens to the standard fire. And so some conclusions that we were able to make, we were able to look at the char depth through the connections as well as through the glulam and the CLT itself. And we were able to see that there definitely is more charring through the connections. We were able to calculate that the char rates in Eurocode for connections are actually unconservative. We saw corner rounding, almost textbook corner rounding, which is when you see like the char creating those rounded edges, and that what was predicted in Eurocode was almost spot on to what we saw in the experiments. We saw that smoldering occurred for almost every single specimen. So every single specimen was flaming when we took it out of the furnace, and the heat continued to propagate through the connections as well as through the glulam itself during the cooling phase. And we actually tested 2 connections per specimen. So we were able to test a caulked and uncaulked connection. We didn't really see a lot of increased behavior or improved behavior with caulking. We saw either similar or slightly smaller char depths with caulked connections. But on the picture on the right, you can see that compression of the char. Nothing was at 90 degrees when we took it out of the furnace. We were able to see that compression of the char due to just the weight of the glulam on that block right there. So we did these 2 projects, all right? So we tested isolated connections or connections within frames, but these aren't real fires. The ASTM E119 fire is not a real fire. It's actually a very intense fire. And a furnace actually is not a real environment, okay? So it doesn't have the right amount of oxygen that we would have within this room, or if there was a fire within this room. So where we're going with this is that these tests were really informative to show what could happen, what is possible, what needs to be studied. And we can further study this in a project that is just kicking off in fire testing, doing large-scale compartment fire testing next summer at the Alcohol, Tobacco, and Firearms Lab in Maryland. We also saw that even though we had like the best lab technicians one could ever ask for, except for the ones at Emerson, at the NRC, we were not able to get perfect fit-ups of these connections at the NRC. There were small gaps, right? And so what is the behavior in those small gaps? Is it the same as a fire exposed surface? Is it not the same as a fire exposed surface? And so through REACTS, we have a project that is kicking off on looking at the fire performance in those gaps. So I'll just cover those briefly before you don't have to hear from me anymore. And so this project, looking at large-scale compartment fire tests, our goal is really to look at a number of different things. We want to address smoldering, sustainability. We want to address emissions. And this is in collaboration with Forest Products Laboratory and ARAP and the EPA. And so we are testing at 3 different scales. We're testing at large scale first next summer. We'll then be testing in at the Forest Products Laboratory. We'll be testing medium scale compartments. Someone asked us what a medium scale compartment was, and we decided the size of a doghouse. So that is a medium scale compartment. And then we will be doing some bench scale tests. And so we want to know what is scalable. What can we learn from scalable tests? Do we always have to do large scale tests, or can we actually perform some of these medium scale compartment fire tests that are much cheaper? Can we actually learn something from our bench scale tests and then actually, scale it up to an actual building environment? Or do we always have to do these large scale tests? So you don't need to read this, but every part of the project is really connected to one another. All the information from one scale is going into another scale. All the information between tasks are going into one another. We will be doing finite element analysis of all the different scales. We will be doing, that includes FDS modeling as well as modeling of the connections themselves. We will be, so this is really experimental, numerical, kind of overarching scalability. So just briefly on the REACTS project, looking at the fire behavior in these cracks as well as in these gaps. This is our amazing technical advisory committee that has been working with us. These tests will occur also at the Forest Products Laboratory. So, between the previous proposal that I told you about and this REACTS proposal, this has created a really great collaboration between OSU and the Forest Products Laboratory. Again, there's students on these projects, right? We need amazing students to go into these labs and learn from the technicians, from the researchers, go work there, and continue that collaboration. So here I'm just showing CLT, but we're looking at gaps in glue connections as well as in CLT panel-to-panel connections, trying to answer these questions that I posed earlier. What is the fire behavior within those gaps? Is it the same as a fire exposed surface, or is it something different? Do we need fire caulking in an 1/8 of an inch gap, or can we get away with something else? And so really trying to answer those questions. Question I have is, how do you numerically model that? So do you just say it's normal air or not? And so, doing these tests and doing repeatable tests will give us enough data to start answering these questions. So I did say there are students. This is every single student in the last 6 years that have worked with me that has been funded by TDI, many of which has come to work for many of your firms. And I do want to highlight them because they were doing all the amazing work that I've highlighted today and talked about today. But we are funding the next generation of mass timber experts, and I think that's really exciting. The last part I'll talk about with education and outreach is collaboration with the Northwest Carpenters Union. They built all of our deformation compatibility tests that we performed at OSU a number of years ago. And so, yes, we need more structural engineers, we need more architects to go work for all of your firms, but we also need people to build the buildings. And we need our structural engineers and architects to understand how to communicate with them and for them to understand how to communicate with us. And so this provided that space. And so working with them, they built all the specimens. So we can say our specimens were built by actual carpenters. It's great. But then our student, Haley Medlin, was communicating with the workers themselves, with the carpenters themselves, and they were communicating back to her. So she got part of her master's degree was learning how to actually operate on a construction site, how to actually communicate with carpenters. And part of their framing class was building her specimens and learning how to communicate with structural engineers. So it was a really great educational experience, and we hope that we can keep collaborating with them in the future. Another education and outreach. So the last 2 years, I've been hosting a mass timber webinar series. You can access it through this QR code. Every single speaker is a woman or underrepresented minority. And we can look around the room today and we see great diversity within the field of mass timber. And this is really exciting and provides examples for young engineers and for young architects to think about what is possible for them. And so if you want to access, all the videos are recorded, all the lectures were recorded, and they're up at this QR code. These are all the products that were developed through the projects that I talked about, funded through TDI. These are conference and journal publications that have been developed with students. And then I keep talking about this fire lab. We're very excited about this. I'm really excited not to have to travel to another country to do fire testing. And so, into the future, hopefully in a few years, I can highlight some tests that we're doing actually on OSU's campus, and you all can come down to OSU's campus to see what a fire test is all about. So thank you very much. Hopefully, I have like 2 minutes for questions.